Hi, in this video, we're going to go over a tree that can store data. We'll call it the FhDataTree. Now, the FhTree that we implemented earlier, it provides a management of the tree structure, but it cannot store any data. Now, we did have these things called labels, but labels are just used to identify the node. It's not supposed to be arbitrary data. So in order to store data, we'll do something very similar to when we implemented the data linked list that will create the data tree node that inherits from the tree node, and we can store data in the data tree node, and then we'll create the FhDataTree that inherits from the FhTree that will provide methods that manages like insert, remove data, and but it will use the node or tree structure management functionality that's already provided by the FhTree. So let's start with the data tree node, which inherits from tree node. And so the main difference now is that the data tree node, the initializer, takes a required data parameter for the kind of, for data, right? And it has the rest of the parameters that the tree nodes would have, like sibling, first child, previous, and the root. Now, the FhTree node, the initializer, also has the label parameter, but like we said, that was only used to identify a node. Now that we have data, we don't really need it. So that's not part of the parameter to the data tree node than the init method. And obviously it calls the supers or tree nodes than the init method. And for the data, it creates a data instance attribute to remember the data that is supposed to store in this node. And for the string method, then but for a node that stores data, we really just care about the data in the node. So we just return a string that represents the data, and that's it. Now, next we can look at the data tree now, which inherits from the tree. And then the init method, well, what kind of information on top of what FhTree needs do we want for the data tree? Well, since we are storing data, maybe perhaps that the client would want us to store one particular type of data. So perhaps they can specify the data, the type of data that they're going to put into the data tree. So we provide a parameter for them. Now, they don't have to say the type of data because, in Python, a container type like list can store heterogeneous data. So they don't have to, but if they do, we'll enforce that. And the first thing we'll do in dunder init, as usual, is to do the super dunder init. And if the client actually specified the data type, so the data type is not none, and in that case, then we have to make sure that the data type does say that it's a type, right? It should not be, say, a number. So to actually, this is kind of interesting, to actually make sure that the data type specify a type, then we can say its instance is data type a type. Okay, so if you put a number like 1, 2, 3 here, then that is not a type. However, if you put things like int or string or something, or user-defined type in here as the data type, then it is a type. So if it's not a type, then we raise a type error. Otherwise, everything is good, and we'll just remember the data type that we can later enforce for the client. Then where we use this data type is in a function that we'll call valid data, just like the valid node. And so given a piece of data, the only thing that we really want to validate is that if our data type is actually specified so that it is not none, then we want to make sure that the data the client wants to add to the tree would be an instance of the data type that it specified in the initializer. So if it's not, then we'll raise a type error. Otherwise, we'll consider it valid data. So again, we are definitely not doing duck typing here. We are checking for types. Now, the next method we want to implement would be analogous to something that we did in the FhDataTree, and that is a method to bootstrap or set the very first node, or in this case, the very first piece of data for this tree. So remember, we have a set root node method in FhDataTree. So in this case, in the data tree, then we'll have a set root data method. And what this set root data method is, it takes a piece of data and will validate the data, make sure it is the right type if the client wants us to do that. And if it is, then we simply wrap the data in a data tree node, and then we set that data tree node as the root of the tree. So with that, we have enough to actually set up a tiny little tree with a single piece of data. So let's make sure that we can do that. Data tree test. So here we just instantiate a data tree. We'll use the data type feature. So we're going to say we will put integers in this tree, and we'll set the root data to the number 0. And let's hope that works. And yes, it does. So it's a tree. It has one piece of data in it, so size is 1, and the data we just put in is the integer 0. So the next thing we want to do is, very naturally, we want to be able to add other data to the data tree, right? Not just setting the root. Now, remember, in the FhDataTree, we have the ability to add a node given a parent node and a child node. So to do something analogous for data tree, then we should probably have a add data method that takes a piece of parent data and the new data that we want to add as a child of the parent data. And the way to implement add data would be something very similar to what we've done so far, that first we validate the new data to be the right type, and then we'll just use its FhDataTree counterpart, the add node, to add the new piece of data that is wrapped inside a data tree node. Now, the question, though, is what can we put as the parent node? Well, so obviously, it should be an existing node that contains the parent data. Now, how do we know what that node is? Well, we don't. Therefore, we really have to search for it. So in fact, I would like to invite you to implement the find data method that will find and return a node in the tree that contains the given data. Now, it is not out of the realm of possibilities at this point, because it is actually very similar to a method that we've already implemented for FhDataTree. So here is your chance to give it a try yourself if you like. And I am going to talk about how we can implement that now. So in order to find a piece of data, there is really no shortcut. We have to look at every single node until we either find the piece of data we're looking for, or we've looked through all nodes and we couldn't find it, right? So visiting or looking at every single node is something that we've already done in our dunder string method, right? That construct a potentially huge string that contains all the nodes in the tree. So we can do something very similar to that in our find method. So remember that in the dunder string method, we created a recursive version of the string. We call it the string recurse, and we call that string recurse from the Dunder string, but we bootstrapped the first call to the recursive version with the root node. So we'll do something very similar for find, that will create a find recurse method, and we will call from find the non-recursive method the recursive version and bootstrapped it from the root of the tree. Now, the find recurse method is going to look very familiar to those of you who remember how the string recurse was implemented. So the parameter it takes is, well, it needs the piece of data that it is looking for, and the node that it should start the searching from. So the base case is that if the node is none, then means the subtree is looking at it, it's empty. Well, so by definition, you cannot find the data in the empty tree, right? So it returns none here. Next thing is that it's going to compare the data it's looking for to the data of the node. And if they are equal, then hey, great. We find the data we're looking for, and we can return the node that contains the data. Now, if that's not the case, then the next thing it should do is it should look to the siblings and look to the children to try to find the piece of data. And now the order in which it does the recursive call, it does not matter in the sense that it will find the piece of data regardless if it starts, with the child or the siblings. If the tree contains the duplicate data, it might find it first in the sibling or might find it first in the child, but it will find it, right? So in any case, so we'll just follow what we did in the string recurse method. We'll just recurse to the children first. So it will call itself and give it the same piece of data that it's looking for, and the node that it's going to look at is the child node, and it remembers the result that it returns. Now, if it returns a node, or if it returns something that is not none, that means it finds the piece of data in its children. So in that case, it's done searching, it can just return the node. Now, if the node that find recurse on the children is none, then it should look to its siblings. And that's all it takes to search through the entire tree for the piece of data. So with the find method implemented, we can complete our implementation of add data, that the parent node that contains the parent data is the node that is returned by self.find. Now, one more detail before we can actually use it, and that is, can we assume we always find the node that contains the parent data? Well, obviously not, right? Because it can be any piece of data, and it might not exist in the tree. So in order to handle that, we have to check the return result of find parent data, right? So we'll assign that value to parent node, and if the parent node is not none, then we can do the add node thing. Otherwise, in our implementation, we'll choose to raise a key error to tell the client that, hey, we cannot find the piece of data, so we cannot attach the new data to the node that contains the parent data. So this is what I've already typed out here. And now we can actually try to construct a more meaningful tree here. And let's hope that it works. And let's see, there we go. So to 0, we attach 3 to 1. So the order, remember, they're added in the reverse. So it's 1, 2, 3. And then to 1, we attach 4 and 5. And to 5, we attach 6, 7, 8, and 9. So that's working as expected. Now, I want to point out a problem with this particular approach that we have chosen to implement add data. So can you think about what problem that might be? This is actually has to do with performance. So what it is that every time we call add data, we have to find the parent node that contains the data, right? Even if we have just found it. So in this case, let's say we are adding all these numbers to the node that contains 5. Well, we don't remember where the node that contains 5 is. Nothing in our code does that. So every time this add data is called, even though we just found the node that contains 5, we have to find that same node again across these different calls. Now, so that means that in a big tree, and especially if the parent node is actually somewhere towards the end of the search, then this can take a really, really long time. So that's a problem. Now, there are ways to help with this problem. So for example, we can keep kind of a cache that maps the value to the nodes. So every time we given a piece of the parent data, we can maybe quickly look up the node that contains that data, or we can keep some sort of state like a self.current node in the tree, and we only allow attaching data to that node. Now, however, in our implementation, we are not going to be implementing any of these mitigating strategies, just because, well, general trees aren't really known for performance to begin with. And I really just want to focus on the functionality and concepts for now. But just know that, yes, there is a problem. Next, I'm going to invite you to implement the remove data method. This would be obviously be using the FhTree's remove node method, and it's very similar to some of the methods that we already implemented. So please pause the video and give this a try. All right, so hopefully you have done that and perhaps have tested it out. And here is my code to do that. So first, we find the data, and hopefully we get the node that contains the data. And if we do, then we basically can just call the FhTree remove node to remove the node that contains the data. Otherwise, we'll just raise the key error telling the client we cannot find the data to remove. So now that we have removed data, we can try to test it out. So here I remove 2, and then I remove 5 from this tree, and let's run it. So this is the original tree, and if we just remove 2, that's just a piece of data with no subtree attached to it. So 2 should be gone. 2 is gone from here, but the rest of the tree is intact. And then we remove 5. Now 5 has a bunch of nodes attached to it, so we should see 5 and the subtree at 5 gone after that. So indeed, that whole subtree is gone now. And finally, let's test one more thing that we should have tested with the add data, but we didn't, and that is to remove a non-existent piece of data, say 100, and it should give us a key error telling us that we couldn't find 100 in the tree. So that is the basic implementation of FhDataTree.